Hey everyone, and welcome to this explainer. So today we're unpacking a seriously pragmatic edge networking architecture. If you've ever wrestled with trying to balance really complex, heavy orchestration on your back end while maintaining ultra-low, lightning-fast latency out on the edge, well, you're absolutely in the right place. We're looking at a system that basically takes the mature, rock-solid stability of Python and pairs it with the absolute blistering speed of VLang. It's a really fascinating look at picking exactly the right tool for the job. Let's get right into it.
Here's a quick look at our roadmap today. 1. The right tool strategy. 2. Our hardened cryptographic network hub. 3. Simulating financial ledger logic. 4. VLang high-speed edge testing. And finally, 5. Unified Docker cluster deployment.
All right, kicking things off with Section 1, the right tools strategy. Now you might be wondering, when engineers see a super fast, shiny new language like VLang, or just V, the immediate temptation is, let's rip out all the old code, let's rewrite the whole backend from scratch. But is that actually necessary? I mean, think about it. Your orchestration stack is already humming along, deployed using Docker containers on a solid Python fast API backend. Tearing all that down just for the sake of using a new language, that's a massive, massive operational risk.
So instead of a risky rewrite, the optimal engineering choice here is a hybrid approach. Think of your existing Python setup as the secure vault, right? It handles the heavy lifting, the really complex orchestration, and all that deep ledger logic. Then you deploy VLang strictly as the armored car. It's this lightning-fast, highly specialized utility daemon operating way out there in the harsh remote environment of a Motorola or a Linux edge gateway. You keep the stability of Python exactly where you need it, and you inject the raw speed of V exactly where it matters most. Best of both worlds.
Moving on to Section 2, Hardened Cryptographic Network Hub.
Now, out on the edge, especially when you're dealing with cellular networks, you literally have to account for cellular handoffs. As these devices bounce between cell towers, network packets can and will get delayed. And hackers absolutely love to exploit those delays. They'll capture an old packet and try to inject it later. A classic replay attack. To protect against this architecture implements a sliding window expiration, and it ties it directly to an X-device timestamp header. Basically, if a packet is too old, the system just automatically drops it. No questions asked.
This builds into a seriously robust security protocol using a really clever linear dependency pipeline. When a request hits the hub, it basically has to survive 3 distinct tests. Step 1, who are you? The system checks the hardware fingerprint against a strict, hard-coded list of approved Motorola or iPhone IDs. Step 2, are you on time? It checks the network delay against that sliding window we just talked about. And finally, Step 3, are you who you say you are? It mathematically verifies an HMAC SHA-256 cryptographic signature. If it fails even one of those checks, boom, instantly rejected.
Let's talk about that sliding window limit for a second. The code sets a timestamp skew allowance of exactly 60.0 seconds. It is remarkably tight. If your packet takes 61 seconds to reach the server, maybe because of a bad cellular handoff, or maybe because of a malicious delay, it is immediately dropped and logged as an expired packet. It's a completely non-negotiable security threshold.
All right, Section 3, Simulating Financial Ledger Logic.
Before the hub can actually process any transactions, it obviously needs to know how much money is available. To do this, it dynamically calculates an available pool. It combines a base available pool of $1,292.50 with a fallback income pool of $9,600 per feet. Put those together and you get a total internal ledger of exactly $10,892.50. This is the financial playground our edge devices are operating within.
Once that balance is locked in, the ledger processes 3 very specific transaction types. First up is an authorization, which checks if there are sufficient funds. If there are, it places a hold on that money. If there aren't, it throws a strict 1804 decline code, an absolute insufficient funds block. Next, we have a clearing transaction, which comes in and actually subtracts the settled asset amount from the available balance. And finally, a reversal transaction, which adds funds right back if a hold happens to be voided. It's basically a complete, self-contained financial state machine running safely inside our Python vault.
Let's pivot to Section 4, VLang high-speed edge testing.
VLang wasn't just chosen to be trendy. It was chosen for one reason: absolute speed. When you're out on the edge, maybe running on some low-power Motorola or Linux hardware, you literally cannot afford bulky runtimes or huge heavy dependencies. You absolutely need ultra-low latency, a zero-dependency deployment, and an incredibly minimal memory footprint to calculate those complex HMAX signatures before that strict 60-second window expires.
And how does V achieve this crazy raw performance? Well, by compiling straight down to human-readable C code. This gives us native computation speed right there on the edge device, speed that totally rivals heavy hitters like C, Go, and Rust. Because it's compiled into a single, standalone executable binary, you literally just drop it onto the edge device and run it. No virtual machines, no massive dependency trees to deal with, just pure, unadulterated performance.
Bringing it all together in Section 5, Unified Docker Cluster Deployment.
So how do we glue all this together? The Docker Compose file creates this beautiful bridge between these two very different worlds. On one side, we have our gateway hub running a Python 3.11 container exposing port 8000. On the flip side, we have our VLang Edge client. And notice this, the V container uses Alpine 3.18, an incredibly lightweight Linux distribution. This container's entire job in life is just to natively compile our V script and execute it against the Python hub.
The true power of this orchestration, it's triggered with literally one single command, Docker Compose up build. You hit enter and the entire system just springs to life. It builds the Python environment, it compiles the V binary on the fly right inside the Alpine container, then the V client computes the secure cryptographic token, packages up the Motorola fingerprint, transmits the payload to the hub, and the second it gets that HTTP 200 OK confirmation back from Python, the Edge container cleanly exits. It is a completely automated end-to-end validation loop.
We've seen how incredibly powerful this architecture is in a staging cluster, but the source leaves us with a really critical thought to ponder here. As you think about taking this multi-node topology out into the wild, into actual real-world production, how are you going to handle the chaos? How will you configure an Nginx proxy to properly route incoming cellular SIM lines? And what exactly happens to your Docker health checks if network latencies suddenly spike way above 100 milliseconds? This architecture gives you the speed and it gives you the security, absolutely. But scaling it globally? Now that is the next great engineering puzzle. Think about how you'd solve that. I hope this explainer gave you a really solid foundation to start from. Thanks so much for joining me.